Welcome to the Deep Dive. We're taking a look today at, well, reality itself, really. We've got sources digging into the cosmos, into relativity, human perception, and the big takeaway seems to be that a lot of what you think is solid and real, it might just be an illusion of scale or how your own mind works. We're going to explore how physics basically forces us to admit our senses, our intuition, they have limits. Pretty profound limits, actually.
Yeah, that's the plan. We'll start with something fairly straightforward, like an optical illusion, something you can literally see messing with your perception. And then we'll sort of ramp it up, looking at objective science, things like time, matter, how life got started. And importantly, we need to grapple with what that science means philosophically. What are the implications?
Okay, let's start with that illusion then, something everyone listening has probably experienced. The moon illusion. You know when the moon is low, near the horizon?
Mm-hmm.
It looks absolutely gigantic, way bigger than when it's high up in the sky. It feels real, that size difference. But it's not. It's totally wrong, isn't it?
It's completely wrong, yeah. It's probably the most famous and reliable optical illusion we know. Scientists call it the moon on horizon illusion. And it's perfect proof right off the bat that your eyes, the sense you rely on most, can flat out lie to you.
So the moon isn't physically changing size or distance.
Nope. Absolutely not. It's the same old moon, same distance, whether it's peeking over a mountain or straight overhead at midnight. The difference is purely psychological. It's about how your brain tries to make sense of the picture it's receiving.
It's trying to build a 3D model from the 2D image on my retina.
Exactly. Your brain's incredibly good at that, usually. It uses cues from the environment. When the moon's low down, it's sitting there next to things you recognize, trees, buildings, hills on the skyline.
Things I know the rough size and distance of.
Right. Your brain has built-in assumptions about those terrestrial objects. It knows a building is, say, a few miles away. But then it sees the moon behind those buildings.
Which is obviously way, way further than a few miles. It's practically at infinity compared to the buildings.
And that's the conflict. Your brain gets these mixed signals, finite distance cues from the buildings, infinite distance cue from the moon. To make sense of it, to reconcile that impossible visual, it kind of forces the moon to appear much larger. It scales it up to fit the scene.
Ah, okay. So when the moon is high up, there are no buildings next to it.
Precisely. No terrestrial anchors, no conflicting depth cues. Your brain just sees the moon against the blank canvas of space and perceives its, let's say, true apparent size.
It's wild that our brains do that automatically. And I love the trick the sources mentioned to prove it's all in your head.
Oh, the bending over trick. Yeah, it's brilliant. If you actually bend down and look at the horizon moon between your legs.
And you're seeing the world upside down.
Right. The illusion just vanishes. Poof, the moon shrinks back to its normal perceived size.
Why does that work?
Because turning the world upside down confuses your brain's object recognition. It doesn't immediately register those shapes as buildings or mountains anymore. Without that context, without those familiar anchors causing the depth cue conflict, the illusion collapses.
Wow. Just flipping your viewpoint proves reality is an interpretation. So, if our eyes can fool us so easily about the moon, it really makes you wonder, what else are we fundamentally getting wrong? Things like motion, time. Maybe our whole sense of reality needs a rethink. That's what we're digging into next.
Okay, so moving from perception to physics intuition. For thousands of years, really smart people were absolutely convinced the Earth was stationary.
Well, and it feels stationary, right? You don't feel like you're hurtling through space.
Exactly. They trusted their immediate local senses. If I can't feel movement, there must be no movement. Makes intuitive sense.
But it's spectacularly wrong. The sources remind us we're actually moving. How fast is it again?
Earth is orbiting the sun at about 18 miles per second.
18 miles a second. That's insanely fast. Like crossing a major city in the time it takes to pour a coffee.
And yet, you have zero, absolutely zero sensation of it. Why? Because the motion is incredibly smooth. Constant velocity. Think about being on a huge cruise ship on a perfectly calm sea or maybe a high-speed train moving smoothly. Inside a closed cabin, could you tell you're moving?
Not unless it speeds up, slows down, or turns. If it's constant, smooth motion, no.
Precisely. Our atmosphere, the ground, us, everything is moving together at that 18 miles per second. There's no relative motion locally to give us a clue. It's inertia.
And that speed isn't just fast. It has to be incredibly precise, doesn't it, for the orbit to work?
Oh, absolutely. It's a knife-edge balance. That 18 miles per second is crucial. If Earth slowed down significantly, the sun's gravity would win and we'd spiral inwards. Game over.
And if it sped up too much?
We'd break free from the sun's gravity entirely. We'd become a vagabond planet flung out into the cold, dark void of interstellar space. Our orbit is this perfect, delicate dance.
Okay, so where we are is precarious. But then there's the when we are. Time. That feels even slipperier. This idea that we all share the same now. That feels fundamental, but relativity says no.
Relativity completely shatters that intuition. The concept you're talking about is the relativity of simultaneity. It's a core part of Einstein's special relativity. And the Andromeda paradox is a great way to try and wrap your head around it.
Okay, walk us through it. Andromeda Galaxy. That's really far away, right?
Immensely far, 2.5 million light years. So the light we see tonight left Andromeda 2.5 million years ago.
Right, ancient history.
Okay, imagine two people, Alice and Bob. They're standing right next to each other on Earth, looking up at Andromeda. Since they're in the same place, looking at light that traveled the same path, you'd think they see the exact same moment in Andromeda's past, simultaneously.
Makes sense so far.
Now, let's have Alice suddenly start running, say, really fast, away from Bob at a constant speed, even just for a short while.
Okay, her state of motion has changed relative to Bob.
Exactly. And according to relativity, because motion affects space-time and because the speed of light is constant for everyone, Alice's definition of now has just shifted relative to Bob's. If they could somehow instantly compare what they see happening now in Andromeda,
They'd see different things, even though they're basically in the same spot on Earth.
they would see events happening in Andromeda that are potentially days apart in Andromeda's time frame.
Hold on. Days apart. Just because one person started moving, how does that work over 2.5 million light years?
It's because simultaneity isn't absolute. Think of space-time like a loaf of bread. A stationary observer like Bob slices it straight across. That's his now. But Alice, because she's moving, slices the loaf at a slight angle. Her slice of now cuts across a different part of the loaf further down. Over that vast distance to Andromeda, even a tiny angle in her slice of now means she's seeing events that, from Bob's perspective, haven't happened yet or already occurred days ago.
Yeah, so my now isn't your now on a cosmic scale. It only feels shared because we're close together and moving at basically the same speed.
That's the core insight. Now is relative. It's an illusion created by our proximity and the finite but incredibly fast speed of light.
Which makes having objective measurements absolutely critical if we want to agree on anything.
Absolutely. And our history of measuring time itself shows how tricky that is. We used to rely on something inherently unstable.
What was the old definition of a second? Something to do with the Earth.
Yeah, until the 1960s, the official second was defined as a specific fraction of the length of the year 1900 based on Earth's orbit and rotation.
But wait, the Earth's rotation isn't perfectly constant, is it? It slows down, wobbles slightly.
Exactly the problem. If your fundamental measuring stick, the Earth's spin, is itself changing, how can you ever measure that change accurately? Your standard is flawed. It's circular reasoning.
So we needed a better yardstick, something completely stable.
We had to go smaller. Much smaller. We offloaded the definition to the quantum world, to the atom. Specifically, we now define the second based on the relates a precise number of times, billions of times per second.
Like a tiny, perfect, natural clock.
An incredibly stable one. That move gave physics the solid, objective foundation for time it desperately needed, completely separate from the messy movements of our planet.
It's fascinating we went from the planet scale down to the atomic scale to find stability. And speaking of scale, we also completely misjudge the Earth's actual shape, don't we?
We do. Our human perspective gets totally skewed by local features. We stand at the Grand Canyon or look up at Mount Everest, and they seem immense, dominating.
So we draw Earth on maps and globes with exaggerated bumps and valleys.
Right. Textbooks often show these huge mountain ranges, but relative to the Earth's actual size, it's roughly 8,000-mile diameter. Those features are minuscule. The entire difference between the bottom of the Mariana Trench and the top of Everest is incredibly small compared to the planet's overall radius.
How small are we talking?
If you could shrink the Earth down to the size of a standard billiard ball, it would actually be smoother than the billiard ball.
Smoother than a billiard ball, seriously.
Seriously. The variations are that tiny on a planetary scale. If some giant cosmic being picked up the Earth billiard ball, they wouldn't even feel the mountains or trenches when running their finger over it.
So cosmically speaking, Earth is basically a perfect sphere. Our intuition just blows the bumps way out of proportion because they look big to us down here.
It's another example of how our localized experience creates a misleading perception of reality, whether it's the moon's size, the flow of time, or the shape of our own world. And this need for a deeper, sort of non-intuitive grasp of things really came to a head when Newton's physics started to, well, wobble a bit.
Newton's laws of gravity worked incredibly well for centuries, mapping the planets.
Yeah.
Where did they finally run into trouble?
In extreme conditions, specifically very close to the sun where gravity is incredibly strong. The planet Mercury, its orbit wasn't quite behaving as Newton predicted.
It deviated slightly.
It's just a tiny bit, but measurably and consistently. Its orbit precessed sort of shifted around faster than Newton's math said it should. Scientists at the time were so locked into the Newtonian view, they actually invented a hypothetical planet inside Mercury's orbit.
They called it Vulcan, right, thinking its gravity was pulling on Mercury.
Exactly. A ghost planet cooked up to save the existing theory. But of course, Vulcan was never found.
Until Einstein came along.
Right. Einstein's general relativity offered a completely different picture of gravity. Not a force pulling across space, but
Mass warping space-time itself,
yeah,
like a bowling ball on a trampoline.
that's the common analogy, yeah. And when Einstein applied his equations based on this warped space-time idea to Mercury's orbit,
It matched perfectly.
perfectly, it explained the deviation exactly without needing any imaginary planets.
So it wasn't that Newton was totally wrong, just incomplete. Einstein's theory was deeper. It included Newton's where gravity is weaker, but also worked in the extremes.
That's how science progresses, ideally. Building on, refining, and sometimes revolutionizing previous understanding. And a cornerstone of Einstein's revolution was the constancy of the speed of light.
Nothing can go faster. That's like the ultimate speed limit.
This absolute cosmic speed limit, it's fundamental to relativity. And when you push gravity to its most extreme, you get objects where even light can't beat the gravity.
You get black holes.
Black holes. Regions where gravity is so intense, the escape velocity, the speed needed to get away, is faster than the speed of light itself.
Since nothing can go faster than light, nothing gets out. Hence, black.
Exactly. It's not just dark, it's a literal hole in the fabric of space-time, defined by this inescapable gravitational pull. And the density involved is just staggering. The sources mention a black hole the size of a golf ball would weigh more than the entire planet Earth.
It's almost impossible to imagine. And falling into one,
Yeah.
the physics gets pretty gruesome, but also weirdly specific.
You're talking about spaghettification.
Spaghettification. It sounds almost comical, but it's deadly serious physics.
It is. It happens because gravity gets much stronger the closer you get. So imagine you're falling feet first towards the black hole center, the singularity. The pull on your feet will be vastly stronger than the pull on your head, just a few feet further away.
So you get stretched, like literally stretched.
Stretched incredibly thin, yes. The difference in gravitational force, the tidal force, overcomes the forces holding your body together. Your spine would probably snap first, likely at the base. You're being pulled apart vertically. But wait, there's more. At the same time, because all the gravity is pulling towards a single point, you're also being squeezed from the sides.
Stretched head to toe and squeezed side to side.
Like toothpaste being squeezed from a tube while also being stretched like taffy. That's spaghettification. You become a thin stream of particles before you even reach the center.
Okay, moving on from that lovely image. Let's talk about creation instead of destruction. Stars. How do they start?
It all comes down to mass. Think about Jupiter. It's huge, mostly hydrogen and helium, like a star, but it's not a star.
It's a failed star, they sometimes call it. Why?
Not massive enough. The sources say if Jupiter had been maybe 5 times more massive.
5 times? That doesn't sound like that much more on a cosmic scale.
It's enough. That extra mass would mean significantly more weight crushing down on the core. More weight means much higher pressure, which means much higher temperature. And when the core temperature hits a critical point, millions of degrees,
Fusion ignites.
thermonuclear fusion kicks in. Hydrogen atoms are slammed together so hard they fuse into helium atoms.
And that process releases energy. That's what powers the star. How does EMC22 fit in?
It's key. When 4 hydrogen atoms fuse into one helium atom, the helium atom actually weighs slightly less than the 4 hydrogens did.
Mass disappears.
It's converted directly into energy. That tiny amount of missing mass, the mass defect, becomes a huge amount of energy according to EMC22. That energy pushes outwards, balancing the inward crush of gravity and makes the star shine for billions of years.
And it's inside these fusion furnaces that the heavier elements get made, right? The stuff we're made of.
Exactly. Everything heavier than hydrogen and helium,
Yeah.
the carbon in your cells, the oxygen you breathe, the iron in your blood was forged inside stars. And then, when massive stars die in supernova explosions, they blast those newly created elements out into space.
Seeding the next generation of stars and planets, including ours. So when they say, we are stardust.
They mean it quite literally. We are made from the ashes of exploded stars.
Okay, so we're made of star stuff. That
Yeah.
connection is amazing. And it makes the story of life starting on Earth even more interesting, especially how quickly it seems to have happened.
Yeah, the timeline for the origin of life keeps getting shorter, which has big implications for how likely life might be elsewhere.
What was the old thinking? That it took maybe 1 billion years after Earth formed for life to get going?
Something like that. But recent fossil evidence, microbial fossils, pushes the record of life back much further, maybe to 3.8, even 3.9 billion years ago.
Okay, but Earth formed about 4.5 billion years ago. That still seems like a decent gap.
But you can't start the clock right when Earth formed. The early Earth was hellish. For the first, say, 600 million years, it was undergoing the late heavy bombardment. Constant, massive asteroid impacts. The surface was molten. No chance for life.
Right, it needed to cool down first. Liquid water needed to be stable.
Exactly. That cooling phase finished around, let's say, 4 billion years ago, and life appears in the fossil record almost immediately after that.
So if life fossils date back to 3.8 or 3.9 billion years, and the planet only became habitable around 4 billion years ago?
The window shrinks dramatically. Life seems to have kicked in within maybe just 100 or 200 million years once conditions were right.
That's incredibly fast on a geological timescale.
It suggests that maybe, just maybe, life isn't some near impossible miracle. Maybe if you have the right ingredients, which we know are common in the universe, and the right conditions, life emerges relatively quickly. Almost inevitably.
And these right ingredients, they're the most common things out there.
Pretty much. If you list the most abundant elements in the entire universe, what do you get? Hydrogen, helium, oxygen, carbon.
Hydrogen, oxygen, carbon, nitrogen are the top 4 after helium, which is inert. Now, list the most common elements in the human body by mass. Let's see, oxygen, carbon, hydrogen, nitrogen.
It's basically the same list. We are made, overwhelmingly, of the most common stuff the universe has to offer. We are not exotic. We are chemically aligned with the cosmos.
That connection is powerful. And there's another connection the sources mention, linking us through molecules to everyone who ever lived.
The water molecule argument. It's a fantastic illustration of scale. The number of water molecules in a single glass of water is just astronomically huge.
More molecules in the glass than glasses of water in all the oceans.
Exactly that comparison. Way, way more. And because water cycles constantly through the environment, evaporation, rain, rivers, bodies, those molecules get thoroughly mixed over time. So the statistical probability is overwhelming. Any glass of water you drink today contains molecules that were once part of the water drunk by, say, Socrates, or Caesar, or anyone.
Whoa. So I've literally ingested molecules that pass through historical figures.
With virtual certainty, yes. The same logic applies to the air you breathe. Air molecules mix globally very quickly. Every breath you take contains atoms that were once exhaled by dinosaurs, by Genghis Khan, by, as the source mentions, even figures like Jesus. We are physically connected through the constant recycling of matter.
It's not just that we live in the universe.
The universe is literally within us. We are part of this vast interconnected system.
Okay, that cosmic connection is one thing. But physics also seems to be pointing towards something even stranger. Maybe simulation. The simulation hypothesis.
Right. This is where things get really mind-bending, pushing the edge of physics and philosophy. Some areas of fundamental physics, like string theory, when they try to describe the absolute bedrock of reality, the mathematics they end up with.
What does it look like?
It looks uncannily like information, like computer code. Specifically, the sources mention Claude Shannon's work on information theory bits, ones and zeros.
The fundamental rules of the universe look like software code.
That's the provocative finding. The equations describing reality at its most basic level seem to resemble error-correcting codes, the kind you'd find in data transmission or computing.
Okay. That feels like either a massive coincidence or
it suggests something profound about the nature of reality. It leads directly into the simulation argument. The argument goes like this. Assume that it's possible for a civilization to become advanced enough to create a completely convincing simulated reality, populated by conscious beings who think they're real.
Like the Matrix, basically, but potentially undetectable from within.
Right. If such simulations are possible, then presumably any advanced civilization could create many of them, maybe millions or billions.
Okay, so there would be countless simulated universes.
For every one original base reality universe. So statistically speaking, if you find yourself in a universe, are you more likely to be in the one unique base reality or one of the potentially zillions of simulations?
The odds would overwhelmingly favor being in a simulation.
That's the argument. Unless we assume that creating such simulations is impossible, or that no civilization ever reaches that stage, then it's statistically probable that we are simulated beings.
And if we are in a simulation, it puts a weird spin on things, like disasters.
Well, you could interpret major unexpected events, pandemics, wars, sudden societal shifts through a cynical lens. Perhaps the simulators, whoever or whatever they are just stirring the pot, introducing conflict or complexity to make the simulation more interesting or to gather data on responses to crises.
That's a deeply unsettling thought. Are we just entertainment for some higher intelligence? Whether we're real or simulated, one thing seems clear. Our human minds are naturally great at dealing with cold, hard data. We seem wired for stories, not statistics.
There's a lot of truth to that. It's described in the sources as an embarrassing inability sometimes. Think about mathematics. Probability and statistics were among the last major branches to be developed formally.
Why is that significant?
It suggests that thinking statistically isn't a native mode for the human brain. It doesn't come naturally. We're much better at cause and effect narratives or simple heuristics.
And this weakness, it gets exploited.
Massively. The entire gambling industry, casinos, lotteries, they run on people fundamentally misunderstanding or ignoring probability, believing in streaks or feeling due for a win against all objective odds.
It's not just casinos, though, is it? Marketing.
Oh, absolutely. Look at advertising. What's often more persuasive? A detailed bar chart showing product superiority based on data.
Or a smiling person saying, "This changed my life. It's the best thing ever."
Exactly. We are swayed by anecdote, by personal testimony, far more readily than by raw statistical evidence. We trust stories, especially from other humans.
This preference for intuition, for narrative, over data,
Yeah.
it must cause problems when people try to understand science itself, right? Especially weird science like quantum mechanics.
Definitely. The double-slit experiment is the classic example of misinterpretation fueled by intuition.
That's the one where electrons seem to act like particles when you watch them, but waves when you don't.
Right. And it gets spun into this idea that human consciousness itself is changing the outcome, that the universe somehow knows it's being watched.
But that's not what the physics actually says, is it?
Not at all. The confusion comes from misunderstanding what watching or measuring means at the quantum scale. To know which slit an electron goes through, you have to interact with it somehow. Usually that means hitting it with a particle of light, a photon.
And hitting a tiny electron with a photon. That's not a gentle tap.
It's a significant collision. That act of measurement, the physical interaction required to get the information, inevitably disturbs the electron and changes its state or path.
So it's the measurement device causing the change, not the observer's mind.
Precisely. It has zero to do with consciousness. It's a fundamental consequence of needing to physically poke the system to learn about it. The electron doesn't care if a human is involved, it just cares about the photon hitting it.
This clash between scientific findings and ingrained beliefs or intuition isn't new, though. History is full of it.
Absolutely. Take Benjamin Franklin and the lightning rod.
Okay, Franklin. Founding father, inventor, lightning rod. Seems practical. What was the issue?
Well, in his time, churches were often the tallest buildings, and they got hit by lightning a lot, often burning down. The prevailing interpretation for many was that a lightning strike was an act of God, maybe divine wrath.
So when Franklin invented the lightning rod, which safely channels the electricity to the ground,
He was accused by some of heresy for daring to thwart the will of God by preventing the lightning strikes. It shows how easily supernatural explanations fill the gaps before science provides a physical one.
and Galileo faced similar resistance, though his problems were maybe more political than purely scientific.
Galileo's troubles were complex. Yes, his support for the heliocentric model, Earth orbiting the sun, went against church doctrine. But lots of astronomers were quietly thinking that way. His real crime, arguably, was how he communicated it. He wrote his famous book, Dialogue, concerning the two chief world systems, not in scholarly Latin, but in everyday Italian.
Making it accessible to everyone, not just academics or clergy.
Exactly. And worse, in the book, he presents the arguments through a dialogue. The character defending the church's official geocentric view. He's portrayed as a simpleton named Simplicius.
Oh, so he basically publicly ridiculed the Pope's position.
Pretty much. Making the official view look foolish and doing it in the vernacular language that was seen as direct defiance and mockery, leading to his trial and house arrest.
It really highlights this tension between science, which constantly questions and evolves, and dogma, which seeks certainty and fixity.
And it leads to that concept we sometimes call the God of the gaps.
Explain that.
If you define God or the divine primarily as the explanation for things we don't yet understand scientifically, the mysteries, the unknowns,
Then what happens as science explains more, like weather patterns or disease or the origin of stars?
then by that definition, the domain of God shrinks. God becomes, as the source puts it, an ever-receding pocket of scientific ignorance. Now, that's just an objective observation about how that specific definition interacts with scientific progress. It's not inherently an argument for or against belief itself, just about that particular way of defining it.
So the real drive shouldn't be to find comforting final answers that might block further inquiry.
Exactly. There's immense value in learning to, as one quote goes, love the questions themselves. If you jump too quickly to an answer, especially one based on faith or intuition alone, you often stop asking questions. Curiosity dies. True understanding seems to come from being comfortable with uncertainty, with standing at the edge of what you know and peering into the vastness of what you don't. Recognizing that more knowledge often just reveals an even larger frontier of ignorance. Hashtag conclusion and final thought.
What a journey. We started with our own eyes tricking us about the moon. We found out now isn't universal. We contemplated death by spaghettification. And then learned we're literally made of star guts, connected by molecules to everyone who ever lived. It really reframes your place in the cosmos.
It does. It underscores how improbable and, frankly, amazing it is to just be alive, to be conscious. Think of all the possible genetic combinations that could exist but never will. You, specifically you, are an incredibly unlikely event, a winning lottery ticket.
And even the familiar sights in our cosmic neighborhood aren't as permanent as they seem.
None at all. Take Saturn's rings. They look timeless, iconic. But astrophysically, they're fleeting. They're likely made of shattered moons or comets captured relatively recently, and gravitational forces and micrometeoroid bombardment mean they'll probably rain down onto Saturn and disappear within maybe, 10 million years or so? A blink of an eye, cosmically.
10 million years. Gone. And our whole idea of where life can exist might be too narrow, too.
It seems increasingly likely. We focus on the Goldilocks zone around stars, where liquid water can exist on the surface. But think about rogue planets. Planets ejected from their star systems during formation, now drifting alone in interstellar space. There might be more of those rogue planets out there than there are stars with planets.
Billions, maybe trillions of them. Just dark and cold.
Dark on the surface, maybe. But they could still have hot cores, powered by radioactive decay like Earth does. Enough internal heat could potentially sustain liquid water oceans beneath icy shells.
Life powered by geology, not starlight.
It's a real possibility. It challenges our sun-centric view of habitability.
The universe always seems to have more surprises. But there's one final, sobering thought from the sources about the limits of knowledge itself, an ultimate boundary.
Yeah, this one is profound. It has to do with the accelerating expansion of the universe. Galaxies are moving away from each other, and the further away they are, the faster they recede.
Okay, like raisins in rising bread dough.
Kind of. But because the expansion is accelerating, eventually, the most distant galaxies will cross a threshold called the cosmological horizon. They will be so far away, and the space between us and them will be expanding so fast that they will effectively be receding from us faster than the speed of light.
Faster than light. But I thought nothing could go faster than light.
Nothing can move through space faster than light, but space itself can expand faster than light. It's weird, but allowed by general relativity. So the light from those galaxies, even though it's still traveling towards us, will never reach us. The space it has to cross is stretching out too quickly.
They effectively disappear from our view. Forever.
Forever. They cross the horizon, and their light can no longer bridge the gap. Now, think about the implications for the very, very distant future. Trillions of years from now. Imagine some civilization arises within our own Milky Way galaxy long after all other galaxies have receded beyond the cosmological horizon.
What would they see when they look up?
Just empty space beyond our local group of galaxies, which will have merged by then. They would have absolutely no observational evidence that other galaxies ever existed. No evidence of the cosmic microwave background, the echo of the Big Bang.
Who would have no idea the universe had a beginning, no clue about the Big Bang at all.
None whatsoever. All the key evidence would be physically inaccessible, carried away by the expansion faster than light. A fundamental truth about the origin and history of their own universe would be permanently erased from their potential knowledge. That is perhaps the ultimate non-negotiable limit to understanding when the universe itself removes the evidence.